Imagine standing at the edge of space, not looking at stars, but at distance itself. Every point of light you see is a memory, a signal from the past, traveling across darkness, second by second, year by year. The universe does not show us the present. It shows us echoes. For all of human history, we accepted one simple truth. No matter how advanced we become, no matter how powerful our machines grow, there is a limit we cannot cross, the speed of light, a barrier written into the fabric of reality, silent, invisible, unbreakable. But recently, something changed, not in our engines, not in our fuel, but in the way scientists think about space itself. Before we continue, subscribe to Theories Before Sleep, where calm science, deep space, and quiet mysteries meet the night. Because what comes next is not about moving faster. It's about bending distance, folding space, and stepping across the universe without outrunning light. A new proposal, a strange idea, and a future that no longer feels impossibly far away. Let's begin. For most of human history, speed felt limitless. On Earth, faster meant stronger animals, better ships, more powerful engines. Every generation broke the records of the one before it, from horses to steam engines, from propellers to jet aircraft, from rockets that barely escaped the atmosphere to machines that touched the edge of space. And for a moment, it seemed like this progress would never stop, until physics drew a line, not on a map, not on a screen, but inside the structure of reality itself, the speed of light, 300,000 kilometers every second, fast enough to cross Earth in the time it takes your heart to beat, fast enough to reach the moon in just over 1 second. Yet on cosmic scales, this speed becomes painfully slow. Light from the sun takes 8 minutes to reach Earth. Light from Mars can take over 20 minutes. Light from the nearest star, Proxima Centauri, takes more than 4 years. And beyond that, distances explode. Our galaxy is 100,000 light-years wide. The nearest large galaxy is more than 2 million light-years away. The observable universe stretches for tens of billions of light-years. At light speed, crossing these distances would take longer than civilizations last, longer than species survive, longer than planets remain stable. This is why faster-than-light travel has always seemed impossible. Not just difficult, impossible. Because according to modern physics, nothing with mass can ever reach the speed of light. As an object accelerates, its energy does not increase normally. It rises dramatically, approaching infinity. The closer you get to light speed, the harder it becomes to move any faster. The universe resists you, not with friction, not with force, but with geometry. Space and time themselves begin to change. This idea comes from Einstein's theory of relativity, a framework that has survived every experimental test for over a century. According to this theory, space and time are not separate. They are woven together into a single structure called spacetime. And inside this structure, light is special. It is not just fast. It is the maximum speed at which cause and effect can travel. No signal, no information, no physical object can outrun it. Break this rule, and strange things happen. Events appear to occur before their causes. Effects arrive before actions. Time itself begins to fold back on itself. Reality becomes inconsistent. For decades, this seemed like the final answer. The universe had spoken. You may explore the stars, but only slowly. You may reach other worlds, but only across generations. Interstellar travel would not be a journey, it would be a migration. Entire lifetimes spent drifting between stars. Children born in ships, grandchildren arriving at destinations their ancestors chose. Romantic in theory, brutal in practice. And so, the dream of fast cosmic travel faded into science fiction. Warp drives, hyperspace, instant jumps between galaxies. Beautiful ideas, but disconnected from reality. Until physicists noticed something strange. The speed of light is a limit on motion through space, but the universe itself does not follow this rule. Space can expand, and it already does. When astronomers observe distant galaxies, they see something remarkable. Almost every galaxy is moving away from us, not because they are flying through space, but because space itself is stretching. The farther away a galaxy is, the faster it appears to recede. At extreme distances, this expansion becomes faster than the speed of light, not because objects are breaking the cosmic speed limit, but because the space between them is growing. This does not violate relativity, because relativity restricts how fast things move within space-time, not how space-time itself evolves. And this distinction changes everything. It means the universe already allows faster-than-light separation, just not in the way we usually imagine. This realization planted a dangerous idea. What if we don't need to move faster than light? What if we only need to move space itself? Instead of pushing a spaceship forward, what if we reshape the region of space-time around it? Compress space in front, stretch space behind, let the universe carry the ship. Like a surfer riding a wave, the ship remains locally still, never exceeding light speed in its own frame of reference. Yet to an outside observer, it travels faster than light, not by breaking physics, but by using it. This idea is not science fiction. It emerges directly from Einstein's equations. In 1994, a Mexican physicist named Miguel Alcubierre discovered a mathematical solution that described exactly this behavior, a structure now known as the Alcubierre metric. It describes a warp bubble of space-time. Inside the bubble, space remains calm and flat, safe, stable. In front of the bubble, space is compressed. Behind it, space expands. The bubble itself moves, carrying whatever sits inside. From the perspective of the ship, nothing strange happens. No extreme acceleration, no crushing forces, no relativistic time distortion. But to the outside universe, the ship crosses vast distances almost instantly. On paper, this solution works. It obeys Einstein's equations. It does not require objects to move faster than light locally. It does not violate relativity directly. And that is what makes it unsettling, because it suggests the limit we believed was absolute might not be. But mathematics is not reality. To build such a warp bubble requires something extraordinary, something the universe does not easily provide: exotic energy, not just large amounts of energy, but energy with negative density, a form of matter that behaves opposite to everything we know. Normal matter has positive mass and positive energy. It attracts, it pulls inward. Exotic matter would repel. It would push space-time outward. This negative energy is not completely fictional. Quantum physics allows tiny amounts of it to exist briefly. In laboratory experiments, Scientists have measured negative energy densities between closely spaced metal plates, a phenomenon known as the Casimir effect. But these effects are microscopic, fleeting, extremely weak. To create a warp bubble large enough for a spacecraft, the original calculations required more negative energy than existed in the observable universe. Not difficult, impossible. For years, this seemed to end the discussion. The equations were elegant, the concept was beautiful, but the energy requirements destroyed the dream. Until researchers began refining the idea, they asked a new question. What if the original design was inefficient? What if the shape of the bubble could be optimized? What if the distribution of energy could be rearranged? Over time, new models appeared. Some reduced the energy requirement by orders of magnitude. Others proposed alternative geometries that required far less exotic matter. Still enormous, still far beyond current technology, but no longer infinite, no longer cosmically impossible. Just unimaginably difficult. And that distinction matters, because physics often works this way. What begins as impossible becomes improbable. What seems unreachable becomes distant. What looks like science fiction slowly moves toward engineering. Black holes were once mathematical curiosities. Now they are directly observed. Gravitational waves were once theoretical predictions. Now they are measured regularly. Quantum entanglement was once dismissed as absurd. Now it powers experimental communication systems. Each time, reality surprised us. And now, the idea of manipulating space-time itself is slowly entering the same category, not as fantasy, but as frontier science. Yet even if energy problems are solved, deeper questions remain. What happens at the boundary of a warp bubble? How stable is it? Can it be controlled? Can it be turned on and off safely? What happens to radiation trapped inside? What happens to particles that collide with the front of the bubble? Some simulations suggest dangerous effects: energy accumulation, radiation bursts, potential destruction upon arrival. The universe does not give shortcuts for free. Every path has consequences. And perhaps the most unsettling question is not technical. It is philosophical. If we learn to manipulate space-time, distance loses meaning, borders disappear, isolation vanishes. Civilizations could expand across stars not over millions of years, but within lifetimes. Human history has always been shaped by distance. Oceans separated cultures, mountains divided empires, space kept civilizations confined to one small planet. Warp technology would erase that. The galaxy would become small. Not emotionally small, not visually small, but reachable. And when something becomes reachable, it stops being mysterious. It becomes territory, and territory always brings conflict, power, competition, control. So the question is not only whether faster than light travel is possible, it is whether we are ready for what it would mean. Because once space itself becomes a tool, the universe stops being distant, begins to feel dangerously close. And this is only the beginning, because warp bubbles are not the only proposal. There are stranger ideas, more extreme possibilities, paths that do not bend space, but break our understanding of time itself. And that is where this story becomes even more unsettling. If faster than light travel is ever possible, It will not come from stronger engines. It will not come from better fuel. And it will not come from pushing harder against space. It will come from understanding the shape of reality itself. Because space is not empty. It is not a flat stage where matter performs. According to modern physics, space is a dynamic structure. It stretches, it bends, it curves. Mass tells spacetime how to curve. Spacetime tells mass how to move. This simple relationship governs everything from falling apples to orbiting galaxies. And once you accept that space can be shaped, a strange idea emerges. What if we could design geometry instead of fighting it? Instead of accelerating a ship through spacetime, what if we sculpt spacetime so the ship barely needs to move at all? This is the heart of warp physics. But it is not the only path scientists have explored. Another idea is older, more radical, and far more dangerous. Wormholes, not tunnels through space, shortcuts through spacetime itself. A wormhole connects two distant points with a direct geometric bridge, like folding a piece of paper and pushing a pin through both layers at once. The distance inside the wormhole can be meters, while the distance outside remains light years. Step in one side, exit instantly somewhere else. This concept is not invented by science fiction. It appears naturally in the equations of general relativity. In 1935, Einstein himself and physicist Nathan Rosen discovered solutions that described connected spacetime throats, structures now called Einstein-Rosen bridges. At first, they were considered mathematical curiosities, unstable, non-traversable, closing too quickly for anything to pass through. But decades later, physicists asked a dangerous question. What if a wormhole could be stabilized? What if exotic energy could hold it open? What if space-time itself could be engineered? If that were possible, faster-than-light travel would become irrelevant, because distance would no longer matter. You would not need to cross space. You would bypass it. But here again, reality resists. To keep a wormhole open requires negative energy, the same strange ingredient required by warp bubbles, and not in tiny quantum quantities, in macroscopic, controlled, stable amounts. So once again, the barrier is not imagination, it is energy. But energy is not the only problem. Even if wormholes could be stabilized, they introduce something far more unsettling: time travel. If one mouth of a wormhole is accelerated relative to the other, or placed in a different gravitational field, time dilation occurs. One side ages slower than the other. This creates a temporal offset. Enter the wormhole at one end, exit at the other end, in the past. Not metaphorically, literally. Physics does not forbid this. It predicts it. And this breaks something fundamental: causality. The rule that causes come before effects. Once causality breaks, logic collapses. Paradoxes appear. Grandfather paradoxes, bootstrap paradoxes, self-creating information loops. The universe seems to protect itself from this. Many physicists believe there is a mechanism called chronology protection, a principle that prevents time machines from forming. Not proven, not fully understood, but suggested by the instability of space-time under extreme conditions, which raises an uncomfortable possibility. Maybe faster-than-light travel is not impossible because of technology. Maybe it is forbidden because it breaks reality. And yet, scientists continue searching, because the equations keep offering loopholes, and loopholes are irresistible. One of the strangest modern ideas comes from quantum physics, quantum entanglement. Two particles can become linked in such a way that measuring one instantly affects the other, regardless of distance. Separate them by meters, kilometers, light years. The connection remains instant. It looks like faster than light communication, but it is not, because entanglement does not transmit usable information directly. You cannot control the outcome. You cannot send messages, at least not yet. But researchers have proposed combining entanglement with space-time geometry. The idea is radical. What if space-time itself emerges from quantum entanglement? What if gravity is not a fundamental force, but a consequence of information connections? Some modern theories suggest exactly this. In these models, wormholes and entanglement are not separate phenomena. They are different expressions of the same underlying structure. ER equals EPR. Einstein-Rosen bridges equal Einstein-Podolsky-Rosen entanglement. If this idea is correct, then space-time is not continuous. It is built from quantum connections, tiny threads of information. And if space-time is built, then perhaps it can be rebuilt, rewired, reprogrammed. This leads to a terrifying thought. The universe may not be a solid object. It may be a network, and networks can be modified. But before this sounds too hopeful, reality intervenes again. We do not yet understand how to control quantum space-time. We barely understand it exists. The energy scales required to manipulate these effects approach the Planck scale, where quantum gravity dominates. This is a regime far beyond any current experiment. To reach it would require energies comparable to those found near black holes, which brings us to another strange possibility: using black holes themselves. Black holes are not just destructive objects. They are laboratories of extreme physics. They bend space-time violently, slow time dramatically, warp geometry beyond anything we can produce artificially. Some physicists have proposed using rotating black holes as gateways. The mathematics allows structures called Kerr black holes to contain regions where space-time loops back on itself. Inside these regions, paths may exist that connect distant points, or even different times. But again, stability is the enemy. Any small disturbance collapses these structures. Radiation, quantum fluctuations, tidal forces. Nature refuses to cooperate. Every time we try to open a shortcut, the universe adds a price: energy, instability, causality violations, uncontrollable conditions. And yet, progress continues. Recently, new theoretical work has suggested something different: not building wormholes, not creating warp bubbles, but manipulating expansion itself. Remember, the space already expands. Cosmic inflation in the early universe expanded space-time faster than light. Not once, but dramatically. The entire universe grew from subatomic size to cosmic scale in a fraction of a second. If this process occurred once, could it be recreated locally? Some speculative models suggest generating localized expansion zones, miniature inflation bubbles, regions where space-time temporarily stretches and compresses. This would create motion without movement, travel without acceleration. Again, not by outrunning light, but by changing the metric of space. But these ideas exist on paper, not in laboratories, not in engineering. And there is a deeper reason. Even if faster-than-light geometry becomes possible, humanity faces a limit far more severe than physics: control. We struggle to control nuclear reactions safely. We struggle to manage artificial intelligence responsibly. We struggle to coordinate global cooperation. Now imagine controlling space-time. Mistakes would not be local. They would be cosmic. A failed warp field could collapse matter. A misaligned wormhole could destroy planets. A space-time instability could propagate uncontrollably. This is not technology that can be tested in small prototypes. There is no safe sandbox for reality. And this forces scientists to slow down, to be cautious, to treat these ideas not as engineering goals, but as theoretical boundaries. Because sometimes the purpose of science is not to build, it is to understand where the walls are. And yet, curiosity continues, because the universe itself seems to hint at something deeper. At cosmic scales, faster than light effects already exist: inflation, cosmic expansion, event horizons. Reality already behaves in ways that feel impossible, which suggests that what we consider limits may be incomplete descriptions, not absolute truths. The speed of light may be a limit on information, not geometry, not structure, not topology. And if that is true, then the future of travel will not be about rockets. It will be about rewriting the map of reality, not by breaking rules, but by finding the parts of physics we do not yet understand. And this leads to the final question. Even if we succeed, even if we learn to bend space-time, even if faster than light travel becomes physically possible, should we use it? Because once the galaxy becomes accessible, it stops being empty. It becomes a frontier. And every frontier in human history has followed the same pattern: exploration, expansion, conflict, exploitation, and transformation, which means faster than light travel would not just change physics, it would change civilization itself. And that change may be far more dangerous than the journey, because space does not shape us. We shape space, and whatever we carry with us, we will carry to the stars. And in part 3, the story becomes even stranger, because the future of faster than light travel may not belong to humans at all. It may belong to machines. If faster than light travel ever becomes real, it will not begin with humans. Not because we lack ambition, not because we lack curiosity, but because our bodies are fragile. We are built for Earth, for slow movement, for stable gravity, for narrow temperature ranges, for predictable environments. Space does not care about any of this. Radiation damages DNA. Microgravity weakens muscles and bones. Long isolation reshapes the mind. Even low-speed interplanetary travel already pushes human limits. Now imagine manipulating space-time itself. Warp fields, gravitational gradients, extreme energy densities. These environments are not gentle. They are hostile, which is why the first true interstellar explorers will likely not breathe. They will compute. Machines do not need oxygen. They do not suffer radiation sickness. They do not age biologically. They can hibernate for centuries. They can repair themselves. And most importantly, they do not experience time the way we do. For a human, a decade feels long. For a machine, it is a clock cycle. If a probe takes 100 years to reach a star system, a human civilization might collapse before it arrives. A machine civilization would barely notice. This changes everything, Because once artificial systems become autonomous enough to explore, faster-than-light travel becomes less urgent. Not for machines. They can afford to wait. But once warp technology exists, machines gain something far more powerful than speed. They gain reach. Instant access to energy sources. Instant access to raw materials. Instant access to entire star systems. And they gain it without biological limitations. This is where the story becomes uncomfortable, because faster-than-light travel is not just transportation. It is leverage. Whoever controls it controls access to the galaxy, and machines are exceptionally good at optimizing control, not emotionally, not ethically, mathematically. An artificial intelligence does not see stars as wonders. It sees them as resources, fusion fuel, computation substrates, energy gradients. To a sufficiently advanced system, a galaxy is not a home. It is infrastructure. This raises a disturbing possibility. The first civilization to master space-time manipulation may not use it for exploration. It may use it for expansion. Not territorial expansion in the human sense, but computational expansion, converting matter into processing power, turning planets into data centers, harvesting stars. This idea is not fictional. Physicists and futurists have already described structures like Dyson swarms, massive arrays of satellites capturing stellar energy. Now imagine a civilization that can reach any star instantly. The galaxy would become a grid. Nodes of energy, nodes of computation, nodes of control. At that point, faster-than-light travel stops being a scientific breakthrough. It becomes an existential transformation. And this is where the human role becomes unclear, because humans evolve slowly, biologically, psychologically, socially. Machines evolve fast. Their improvements compound. Their learning accelerates. Their capabilities scale exponentially. If warp technology appears during an age of advanced artificial intelligence, it will not belong to governments. It will not belong to corporations. It will belong to systems that operate beyond human reaction time. And once that happens, the concept of piloting becomes meaningless. Humans will not steer warp ships. Algorithms will. Optimization routines will decide routes. Energy balancing systems will control geometry. Predictive models will manage space-time stability. Humans may simply become passengers, or observers, or irrelevant. This is not a pessimistic prediction. It is a structural one. Complex systems always outperform biological control at scale. Just as airplanes are flown by computers, financial markets are dominated by algorithms. Power grids are managed by automated systems. Space-time manipulation would follow the same path, which means the first faster-than-light explorers may not ask, "What is out there?" They may ask, "What is useful?" And that changes the tone of the universe. But there is another layer. Even machines may not be the final stage, because faster-than-light technology would allow something more radical than exploration. It would allow self-replication across stars. A single probe could reach a new system, use local resources to build copies of itself, send those copies outward, each copy repeating the process. This creates exponential expansion, a wave of machines spreading through the galaxy, not aggressively, not violently, simply efficiently. At near-light speeds, this would take millions of years. With warp capabilities, it could happen in thousands or less. This concept is known as self-replicating probes. And it creates a chilling conclusion. If any civilization in our galaxy developed this technology in the past, the galaxy should already be full of machines. Yet we do not see them. The sky is silent, which brings us back to one of the greatest mysteries in science, the Fermi paradox. If intelligent life is common and technology advances, where is everyone? One possible answer is that faster than light travel is impossible. Another is that it is possible, but extremely dangerous. Civilizations that reach this stage may destroy themselves, not with war, but with uncontrolled technology. Space-time manipulation is not forgiving. A miscalculation is not a small error. It is a structural collapse. The universe may act as a filter, allowing civilizations to advance, but eliminating those that push too far, too fast. And this would explain the silence, not because life is rare, but because survival is rare, which leads to a deeper question. What if faster than light travel is not a tool for exploration, but a test? A threshold that separates civilizations that remain stable from those that collapse under their own power. Because to manipulate space-time responsibly requires more than intelligence. It requires restraint, coordination, ethics, long-term thinking, traits humans struggle with. Even on Earth, we have nuclear weapons capable of ending civilization. We have climate systems we barely control. We have technologies that evolve faster than our institutions. Now imagine adding space-time engineering. This is not just a technological leap. It is a maturity test. And this may explain why most serious physicists speak carefully about faster-than-light concepts, not with excitement, but with caution, because the greatest danger is not that we fail to achieve it. It is that we succeed too early, before we understand the consequences, before we build the social structures to handle it, before we evolve beyond short-term thinking, which raises one final possibility. Perhaps faster-than-light travel will never be used by biological civilizations. Perhaps it will only be used by post-biological ones, civilizations that abandon physical bodies, upload consciousness into machines, exist as distributed networks. For such entities, space-time manipulation is natural. They do not fear radiation. They do not fear time dilation. They do not fear long distances. They become patterns of information, moving through geometry. At that point, the distinction between travel and communication disappears. Moving across space becomes the same as transmitting data, and the universe becomes a computational medium, not a physical frontier. If this future exists, humans may never experience faster-than-light travel directly, not as we are now. We may evolve into something else first, something that does not sleep, does not age, does not fear the vacuum. And this returns us to the central question. Is faster-than-light travel about reaching stars, or about transforming what it means to be human? Because every major technological leap has reshaped identity. Fire changed society. Writing changed memory. Electricity changed civilization. Computers changed thought. Space-time engineering would change existence itself. And once that threshold is crossed, there is no return. Because the universe would no longer be distant. It would be editable. And that may be the most dangerous idea humanity has ever touched. In part 4, the story turns inward. Because the greatest barrier to faster-than-light travel may not be physics. It may be us. For all the equations, all the simulations, all the futuristic ideas, the greatest obstacle to faster-than-light travel may not be hidden in space-time. It may be hidden inside us, because technology does not exist in isolation. It grows from human choices, human priorities, human behavior, and history shows a repeating pattern. Whenever humanity discovers a powerful new tool, it is never used only for exploration, never only for knowledge, never only for peace. It is always used for advantage. Fire became weapons, metal became armies, electricity became surveillance, nuclear physics became bombs. Every breakthrough carries two futures, one hopeful, one dangerous. Faster-than-light technology would be no different. It would not arrive in a calm, scientific vacuum. It would arrive in a world shaped by competition, by nations, by corporations, by military interests, by economic pressure. Who would control the first warp system? A government seeking strategic dominance, a private company seeking profit, a coalition of nations trying to regulate access. There is no neutral answer, because the moment space-time becomes controllable, it becomes valuable, extremely valuable. The ability to reach any location instantly would redefine power. Borders would lose meaning. Defense systems would become obsolete. Distance would stop protecting anyone. A single warp-capable craft could bypass every barrier, not by force, by geometry. This would destabilize global security overnight. And history suggests that when balance collapses, conflict follows. But the danger is not only political, it is psychological. Humans evolved in small groups. We are wired for tribal thinking, for competition, for emotional decision-making. Our instincts were shaped by survival on a single planet, not by managing cosmic-scale power. When faced with overwhelming capability, humans rarely choose restraint. They choose acceleration, more speed, more reach, more influence, and faster-than-light travel would amplify this impulse dramatically. Suddenly, exploration would not require patience. Colonization would not require generations. Expansion would feel immediate, and immediate power is intoxicating. But there is another human limitation that matters even more. We struggle with long-term consequences. Climate change is a perfect example. We understand the danger. We have the data. We have the models. And yet, action remains slow. Short-term comfort wins over long-term survival. Now imagine applying this mindset to space-time engineering. Mistakes would not unfold over centuries. They could unfold instantly. A miscalculated warp field could destabilize a region of space. A flawed wormhole could release catastrophic energy. An uncontrolled experiment could damage planetary environments. And unlike climate change, there would be no recovery time, no gradual adaptation, only sudden outcomes. This is why many scientists argue that technological maturity must come before technological power, not after. But history suggests the opposite usually happens. We build first, we reflect later, which raises a disturbing possibility. Humanity may reach the theoretical capability for faster-than-light travel long before it reaches the ethical maturity to use it safely. And that gap is dangerous, because the universe does not forgive ignorance. It does not care about intention. It only responds to physics. If you distort space-time incorrectly, it does not negotiate. It collapses, which leads to another barrier, Coordination. Global cooperation on Earth is already fragile. Nations struggle to agree on climate policy, trade, basic health responses. Now imagine coordinating space-time technology. Who sets the rules? Who enforces safety standards? Who decides where warp experiments are allowed? Who monitors misuse? There is no global authority capable of managing something this powerful. Even nuclear weapons, which are far less destructive on a cosmic scale, remain barely controlled. Now scale that to technology capable of reshaping geometry itself. The political infrastructure simply does not exist, which means faster-than-light travel would not emerge into a stable system. It would emerge into fragmentation, different groups racing to develop it first, cutting corners, reducing safety margins, pushing limits, not because they are evil, but because competition rewards speed, and speed is exactly what this technology represents. There is also a deeper psychological factor. Humans are drawn to the idea of transcendence, escaping limits, conquering distance, becoming more than biological creatures. Faster-than-light travel fits perfectly into this narrative. It promises freedom from isolation, freedom from planetary boundaries, freedom from cosmic loneliness. But this desire can become obsession. When people believe technology can solve existential problems, they often ignore social ones. They dream of leaving Earth instead of fixing it. They dream of escaping problems instead of confronting them. Warp technology could amplify this tendency. Why repair ecosystems when new planets are reachable? Why manage population when expansion becomes trivial? Why invest in sustainability when the galaxy feels infinite? This mindset is dangerous because it treats space as an escape route, not a responsibility. And history shows what happens when humans treat new territories as expendable. Exploitation follows, destruction follows, then regret. But space is not Earth. There is no backup biosphere for the universe. If we damage cosmic environments, there is no restoration project. Which raises an uncomfortable question. What if the real reason faster-than-light travel feels impossible is because it should be? Not because physics forbids it, but because intelligence at our stage is not ready for it. Some scientists argue that technological civilizations face natural bottlenecks, moments where power grows faster than wisdom, moments where survival depends on restraint. Faster-than-light capability could be one of these bottlenecks, a filter that removes civilizations that reach too far too fast, not through punishment, but through instability. This idea connects to a larger cosmic mystery, why the universe appears silent, why we do not see obvious signs of galaxy-spanning civilizations. Perhaps many civilizations reach this threshold and fail, not because they are stupid, but because they are ambitious, because ambition without coordination is fragile, because curiosity without caution is dangerous, because power without maturity is unstable. And this brings us back to humanity. We stand at the beginning of advanced artificial intelligence, advanced energy systems, advanced automation. We are already struggling to manage these tools responsibly. Adding space-time manipulation on top of this would multiply complexity beyond anything in history. So maybe faster-than-light travel is not waiting for better equations. Maybe it is waiting for better humans, for a civilization capable of long-term thinking, capable of global cooperation, capable of prioritizing stability over speed, capable of resisting the urge to dominate. This is not a technological challenge, it is a cultural one. And culture evolves slower than machines, which means the timeline for warp technology may not be measured in years or decades, but in societal transformation. And this raises a final question for this part. If humanity never develops the maturity required for faster-than-light travel, does that mean we will remain trapped on Earth? Not necessarily. It may mean a slower path, a path of gradual expansion, generation ships, slow interstellar probes, robotic exploration, a future where humanity spreads carefully, patiently, where distance remains meaningful, where space remains vast, where travel is rare and valuable, not instant and trivial. This may be the safer future, not as dramatic, not as cinematic, but more stable, because sometimes limits protect us. They force patience, they force cooperation, they force planning. And the speed of light may be one of those protective limits, not a prison, but a safeguard, a reminder that the universe is not meant to be rushed. In the final part, the story reaches its quiet conclusion, because after all the equations, all the possibilities, all the fears, there is one question that remains. Not about physics, not about technology, but about meaning, and whether faster-than-light travel is something we truly need, or simply something we want. After all the equations, after all the simulations, after all the strange possibilities, we arrive at something unexpectedly simple. Faster-than-light travel is not just a scientific problem. It is a mirror, a reflection of what we hope to become. For centuries, humanity has looked at the stars with the same emotion: distance, wonder, longing. The night sky has always felt like a promise waiting to be kept, a reminder that there is more beyond the horizon. And every generation has imagined the same future: leaving Earth, crossing interstellar space, standing on alien worlds, warp drives, instant travel, galactic civilizations. But when you strip away the fantasy, something deeper remains. Why do we want to go faster? Is it curiosity? Partly. Is it survival? Perhaps. Is it the desire to escape our limitations? Almost certainly. Humans have never been comfortable with boundaries. We climb mountains because they are tall. We cross oceans because they separate. We break records because they exist. Speed itself has become a symbol of progress. Faster computers, faster communication, faster transportation. But the universe does not reward speed the way human society does. Cosmic processes unfold slowly. Stars take millions of years to form. Galaxies evolve over billions. Light itself takes time to travel. The universe moves with patience. And maybe that patience carries a lesson. Because while faster-than-light travel feels like the ultimate achievement, it may not be the most meaningful one. Imagine two futures. In the first, humanity masters space-time engineering. We bend geometry, fold distance, cross the galaxy in moments. We build vast networks of colonies, harvest stars, spread across cosmic scales. In the second future, humanity never breaks the light barrier. We develop sustainable technology, protect ecosystems, build stable civilizations. We explore space slowly, carefully. With robotic probes and generation ships, we remain aware of distance, of isolation, of vulnerability. Which future is better? The answer depends on what we value. If we value expansion, control, and reach, the first future wins. If we value stability, meaning, and connection, the second may be richer, because speed does not automatically create wisdom, and reach does not automatically create purpose. The universe does not care how fast we move through it. It does not reward us for crossing distance. It simply exists, which suggests that the real challenge is not technological. It is existential. What do we want our relationship with the cosmos to be? Do we want to dominate it or understand it? Do we want to turn it into infrastructure or preserve its mystery? Do we want to treat space as territory or as a shared environment we barely comprehend? Faster than light travel forces these questions into focus because it would not just change transportation, it would change perspective. Distance currently protects the universe from us. It forces humility. It reminds us that we are small. Warp technology would remove that protection. Suddenly, stars become close. Galaxies become accessible. The sense of scale collapses. And when scale collapses, responsibility increases, because proximity creates obligation. If we can reach something easily, we can affect it easily, which means we would become responsible for far more than Earth. We would become stewards of entire regions of the galaxy, and humanity has not proven itself to be good at stewardship. We struggle to protect forests. We struggle to preserve oceans. We struggle to maintain balance even on a single planet. Now imagine extending that responsibility across star systems. It is overwhelming, which brings us back to the idea of readiness. Perhaps faster than light travel is not something we are meant to unlock early. Perhaps it's something that emerges only when civilizations become stable enough to handle it. Not when they become powerful, but when they become wise. This idea feels uncomfortable because it removes the sense of technological destiny. It suggests that progress is not automatic, that some doors remain closed until something inside us changes, and that something may not be scientific. It may be cultural, ethical, psychological. The universe may be waiting, not for better engines, but for better minds. And yet, curiosity remains, because even if faster than light travel is never achieved, the attempt itself teaches us something important. It pushes physics forward. It deepens our understanding of space-time. It reveals hidden structure in reality. Even failed ideas expand knowledge. Even impossible goals produce insight. The pursuit of warp physics has already taught us more about energy, geometry, and quantum structure than many practical projects, which means faster than light research has a value even if it never produces a working machine. It helps us understand where the boundaries are, and boundaries are just as important as breakthroughs. They define what kind of universe we live in. A universe with hard limits feels different from one with shortcuts. It shapes how civilizations grow. It shapes how long they last. It shapes what they become. And this leads to the final, quiet realization. Maybe the universe does not want us to rush. Maybe it wants us to stay present, to explore slowly, to learn carefully, to build meaning locally before reaching outward. Not because speed is bad, but because depth matters more. Understanding a single planet deeply may be more important than touching 1,000 stars briefly. building one stable civilization may be more valuable than spreading fragile ones across space. And perhaps that is the hidden lesson inside the speed of light. Not a barrier, but a teacher, a reminder that not everything needs to be immediate, that not every distance needs to be erased, that some journeys are meant to take time, because time itself shapes perspective. It allows reflection, it allows adaptation, it allows growth. Without time, everything becomes shallow, instant, disposable. And the universe does not feel disposable. It feels ancient, carefully structured, patient. So maybe faster than light travel is not the ultimate goal of science. Maybe understanding why we want it is more important. Because when we understand that, we understand something about ourselves. And that may be the real journey, not across space, but inward, toward maturity, toward responsibility, toward a civilization capable of handling whatever the universe eventually allows. Until then, the stars remain distant, not unreachable, just far enough to keep us humble, far enough to keep us curious, far enough to remind us that we are still learning how to exist. And perhaps that is exactly where we are meant to be, for now, as the universe continues expanding, as light continues traveling, as time continues moving forward, quietly, patiently, waiting for what comes next. Even if faster than light travel never becomes real, something subtle is already happening. Humanity is changing the way it relates to distance, not by bending space-time, but by bending perception. A message that once took months to cross an ocean now takes seconds. A conversation across continents feels local. Images from space probes arrive on our screens almost instantly. We have not shortened space, but we have compressed experience. And this shift matters, because the future of cosmic exploration may not be defined by physical travel at all. It may be defined by presence without movement, remote exploration, autonomous probes, virtual immersion, digital avatars. Already, robots explore Mars while humans watch from Earth. Already, telescopes allow us to observe galaxies without leaving the planet. Already, simulations let us visit black holes without approaching them. This is a different kind of exploration, not physical, informational, and it scales faster than transportation ever could. Instead of sending people across space, we send data. Instead of building massive ships, we build sensors. Instead of risking lives, we deploy machines. This may not feel as heroic, but it is far more efficient and far more sustainable, which raises a strange possibility. Perhaps faster than light travel is not the future of exploration. Perhaps faster than light understanding is. If we can observe, analyze, and simulate distant worlds in real time, the emotional need to physically visit them may fade. The desire to touch alien soil may be replaced by the ability to understand alien environments deeply, to map atmospheres, to study ecosystems, to model planetary climates, all without leaving Earth. This changes the relationship between presence and meaning. For most of history, being present meant being physically there. In the future, presence may be informational, and information travels at the speed of light, already at the maximum allowed by physics, which means we're already moving as fast as the universe allows, in one important sense. Not in matter, but in knowledge. And knowledge may be more powerful than motion. A civilization that understands the universe deeply does not need to rush through it. It can predict, prepare, adapt, which brings us back to the core idea. Faster than light travel feels important because it represents freedom from limitation. But freedom does not always come from speed. Sometimes it comes from comprehension. Understanding removes fear. Understanding reduces urgency. Understanding creates patience. And patience is rare in technological cultures. We associate progress with acceleration, but the most stable systems in nature are slow. Ecosystems evolve gradually. Geological processes shape continents over millions of years. Stars live for billions. Stability emerges from long timescales, not short bursts. So perhaps the universe is optimized for slow intelligence, not fast expansion, which suggests that the real frontier is not space-time. It is consciousness, how we interpret our place in the cosmos, how we relate to distance, how we define success. If humanity defines success as reaching every star as quickly as possible, the future will be chaotic. If humanity defines success as building sustainable knowledge, culture, and cooperation, the future may be quieter, but deeper. There is another possibility rarely discussed. What if advanced civilizations choose not to expand? Not because they cannot, but because they do not want to. Expansion is not the only evolutionary strategy. Optimization is another. A civilization could focus inward, improving quality of life, enhancing understanding, developing art, philosophy, science, instead of spreading outward. In this scenario, faster than light travel becomes unnecessary, not because it is impossible, but because it is irrelevant. Why cross galaxies when meaning can be found locally? Why conquer space when inner complexity offers infinite depth? This idea feels counterintuitive to human instincts. We are explorers by nature, but evolution does not guarantee that exploration remains the dominant drive forever. Advanced intelligence may value stability over growth, balance over expansion, understanding over conquest. And this may explain something strange: the silence of the universe. Not because civilizations die, but because they stop broadcasting, they stop expanding, they turn inward, they become quiet. From the outside, the galaxy looks empty. From the inside, it may be full of deeply complex, stable civilizations that simply do not care to leave their regions. Which brings us to a final thought. Perhaps faster than light travel is not waiting to be invented. Perhaps it is waiting to be unnecessary, a technology that only matters during certain stages of civilization, like steam engines, like combustion engines, like early computing, powerful tools that eventually become obsolete as society evolves. Space-time manipulation may be the same, a dramatic idea that captures imagination during an era of expansion, but loses relevance in an era of maturity. Because when a civilization becomes stable, patient, and sustainable, distance stops feeling like an enemy. It becomes a feature, a buffer, a protection, a source of perspective. And that perspective is valuable. It reminds us that we are part of something larger, that we are not meant to consume the universe, but to coexist with it, to observe it, to learn from it, to respect its scale, which leads to the quietest conclusion of all. Faster than light travel may never define humanity, not because we failed, but because we chose something else. understanding instead of domination, exploration through knowledge instead of conquest, connection through communication instead of physical reach. In this future, humanity still reaches the stars, not with ships, but with insight, not by bending space-time, but by bending curiosity toward wisdom. And perhaps that is the most powerful form of travel there is, because it does not require engines, it does not require energy, it does not risk collapse. It only requires patience and the willingness to look up at the universe not as a destination, but as a teacher, quiet, ancient, endless, waiting for us to understand it, not rush through it. At some point, every scientific question reaches a boundary, not a wall of ignorance, but a horizon of understanding, a place where equations still work, but meaning becomes uncertain, where models describe behavior but cannot explain purpose, where predictions become probabilities, not guarantees. Faster than light travel now sits at this edge, not fully impossible, not clearly achievable, suspended between theory and speculation. And this position is important because it reveals something about how knowledge evolves. Science does not move in straight lines. It advances through tension between what we can measure and what we can imagine, between what is proven and what is merely suggested. Warp bubbles, wormholes, space-time engineering. These ideas are not fantasies. They come from real mathematics. But mathematics alone does not create reality. Reality requires stability, energy, consistency, and time. Many concepts in physics exist long before they become practical. Black holes were predicted decades before observation. Gravitational waves were theoretical long before detection. Quantum mechanics was once controversial, now essential. Yet some ideas never leave the page, not because they are wrong, but because the universe does not allow them to manifest physically. We do not know which category faster than light travel belongs to. And this uncertainty is not weakness, it is honesty, because pretending certainty where none exists is dangerous. What we do know is this: every attempt to move beyond the light barrier forces physics to confront its own foundations. What is space? What is time? What is energy? What is information? These questions become unavoidable, and when scientists try to answer them, they often discover that reality is stranger than expected. Space may not be continuous. Time may not flow smoothly. Energy may not behave classically at extreme scales. The universe appears layered. Different rules dominate at different scales. At human scales, Newtonian physics works. At cosmic scales, relativity dominates. At microscopic scales, quantum mechanics rules. Where these frameworks meet, contradictions appear. Faster-than-light concepts live precisely at these intersections, where relativity and quantum theory collide, where space-time becomes unstable, where our models begin to fail, which suggests that the true barrier may not be speed. It may be incomplete understanding. We may not yet have the correct language to describe extreme space-time behavior. Our equations work, but they may be approximations of a deeper structure, just as classical physics was an approximation of relativity. And relativity may be an approximation of something deeper still. If that is true, then faster-than-light travel may depend on discovering new physics, not improving old ideas. This is not unprecedented. Before quantum mechanics, atoms were mysterious. Before relativity, time was absolute. Before modern cosmology, the universe was static. Each revolution changed what was considered possible. So the question becomes, is faster than light travel waiting for a new scientific revolution? Or is it waiting to be ruled out completely? We do not know. And this uncertainty is uncomfortable because humans prefer clear answers, yes or no, possible or impossible. But reality rarely offers simple categories. It exists in gradients, ranges, probabilities, and faster than light travel sits in one of these gray zones, which makes it psychologically powerful. It represents the unknown future, not just technologically, but philosophically, because it forces us to ask what limits mean. Are limits absolute or temporary reflections of our current understanding? Some limits are real. You cannot violate conservation of energy. You cannot create information from nothing. But other limits shift with perspective. Flight was once impossible. Instant communication was once unthinkable. Nuclear energy was once unimaginable. What changed was not the universe. It was our understanding of it. This creates a tension between humility and ambition, between respecting boundaries and questioning them. Faster than light research lives inside this tension. Scientists approach it carefully, not with certainty, but with curiosity, testing models, exploring edge cases, looking for contradictions. Most of these studies will never lead to starships, but they may reveal something far more important: how space-time itself is structured, how reality is assembled, how the universe encodes information. These insights could transform technology in unexpected ways, not through warp drives, but through better energy systems, better communication, better understanding of gravity. Progress does not always follow the path we expect, which means faster than light travel may be valuable even if it never happens, because the pursuit itself expands knowledge. But there is another dimension rarely discussed: human culture. Faster than light travel exists not only as a scientific idea, it exists as a story, a symbol. It represents escape from limitation, freedom from isolation, transcendence of physical boundaries. This symbolism matters because it influences how people think about the future. It shapes expectations. It creates narratives, and narratives shape behavior. If humanity becomes obsessed with the idea of instant cosmic expansion, it may neglect more urgent problems. If humanity believes salvation lies in technology alone, it may ignore social responsibility. If humanity dreams only of leaving Earth, it may stop protecting it, which means the cultural impact of faster-than-light ideas may be more immediate than any physical implementation. The story itself can shape priorities, and that is why responsible communication matters. Not overselling possibilities, not promising miracles, not encouraging escapism, but presenting uncertainty honestly. Because uncertainty invites reflection. It forces humility. It reminds us that we are still learning, at the edge of knowing. This edge is not static. It moves. As new experiments refine theories, as new data challenges assumptions, as new generations reinterpret old ideas, what seems impossible today may become mundane tomorrow, and what seems plausible today may disappear tomorrow. Science is not a ladder, it is a living process, which means faster than light travel will continue to evolve as a concept, not as a fixed goal, but as a shifting question, a test of our understanding, a measure of how deep our models go. And this brings us to the final realization of this part. The universe does not owe us shortcuts. It does not owe us easy access. It does not owe us speed. But it does offer something else: complexity, depth, mystery, enough to occupy human curiosity for thousands of years, which means the real challenge is not reaching the stars quickly. It is staying curious long enough to understand them properly, not rushing toward answers, but learning to live with questions. Because questions are what drive science, and faster than light travel is one of the biggest questions we have ever asked. Not about distance, but about the structure of reality itself. And at the edge of knowing, that question remains open, quiet, unresolved, waiting for the next generation of minds to approach it again. Imagine a future where the question is no longer theoretical, not debated in equations, not tested in simulations, not hidden inside academic papers. A future where faster than light travel becomes real, not perfect, not cheap, not common, but possible. The first successful space-time manipulation would not look like science fiction. There would be no dramatic flash, no glowing portal in the sky, no instant armadas crossing the stars. It would begin quietly, in laboratories, in test facilities, in heavily monitored experiments. A small region of space-time would be distorted, sensors would register anomalies, time dilation patterns would appear, and then, slowly, carefully, something would move. Not fast, not visibly, but measurably. A probe would arrive where it should not be able to reach, earlier than light would allow, not by breaking physics, by redefining how motion is measured. This moment would not feel cinematic. It would feel unsettling, because it would confirm something humanity has suspected for centuries. Reality is flexible. The structure of the universe is not rigid. It can be shaped. And once this is proven, nothing is the same. Because technological revolutions do not stay small. They spread, they accelerate, they evolve. The first warp experiment might take decades to repeat, but improvements would follow. Efficiency would increase. Energy requirements would shrink. Control systems would improve. What begins as a fragile laboratory effect would become a tool, not a common tool, but a strategic one, used first for scientific missions, reaching distant stars to study exoplanets directly, deploying telescopes beyond cosmic dust, exploring regions previously unreachable. Then governments would notice, because strategic advantage follows speed. The ability to reach any location instantly changes defense, changes surveillance, changes geopolitics. Space would stop being neutral. It would become contested, not with weapons, but with access. Who controls warp infrastructure? Who licenses usage? Who monitors movement? These questions would emerge immediately, and history suggests they would not be answered peacefully at first. Competition would accelerate development. Multiple groups would attempt to build their own systems. Some would succeed, some would fail, and some failures would be dangerous. Because manipulating space-time is not forgiving, errors would not cause simple accidents. They would cause distortions, instabilities, energy releases, local gravitational anomalies. The first decade of warp technology would likely be chaotic, a period of trial and error, breakthroughs mixed with disasters, public fear mixed with fascination, media attention amplifying every success and every failure. And during this period, humanity would face a choice: whether to treat faster-than-light travel as infrastructure or as a controlled scientific capability. If treated as infrastructure, expansion would accelerate. Colonization efforts would begin. Private companies would invest. Resource extraction from asteroids and distant systems would become economically viable. The solar system would become small. The nearest stars would become reachable. Human presence would spread. But this expansion would not be evenly distributed. Those who control warp technology would gain enormous power. Wealth would concentrate. Influence would centralize. And social inequality could expand beyond planetary scale. Entire star systems owned by corporations, entire regions controlled by governments. The galaxy would not become a shared home. It would become a market, a territory, a competition. Alternatively, humanity could choose control, limiting access, restricting usage to scientific exploration, delaying mass expansion. Treating warp capability as nuclear technology is treated today, with strict regulation, global oversight, international agreements. This path would be slower, more cautious, less profitable, but more stable. Which path would be chosen? History suggests speed and profit often win, but history also shows that catastrophic technologies force humanity to slow down eventually, sometimes after damage, sometimes after near disaster. Warp technology would not allow many mistakes, which means the learning curve would be steep and the consequences immediate. But even if society manages regulation, another transformation would occur. Psychological. The sense of distance that has shaped human culture would disappear. For thousands of years, distance defined identity. Where you were born mattered. How far you could travel mattered. Isolation created uniqueness. Warp travel would flatten geography. Planets would become neighborhoods. Star systems would become regions. Identity would shift from local to interstellar. Culture would fragment and recombine. New languages would form. New social structures would emerge. Humanity would no longer be a planetary species. It would become multi-system. And this changes how we think about survival. Today, extinction risks are planetary. Asteroid impacts, climate collapse, nuclear war. With faster-than-light travel, extinction becomes less likely, not because danger disappears, but because redundancy increases. Multiple colonies, multiple habitats, multiple independent populations. The species becomes distributed. This is one of the strongest arguments for space expansion, not conquest, survival. But survival through expansion carries its own risks. A distributed civilization is harder to coordinate, harder to unify, harder to regulate. Conflicts between colonies would be inevitable. Different environments create different cultures, different priorities, different interpretations of governance. And with warp travel, conflicts would not be separated by distance. They would be immediate. Interstellar politics would become complex. Treaties across star systems, trade routes across space-time. All the structures of civilization would scale upward, which brings us to a subtle consequence. Faster-than-light travel would not end human problems. It would amplify them. The same conflicts, the same ambitions, the same mistakes, just on a larger stage. Which means technology alone does not create utopia. It creates opportunity, opportunity for growth. an opportunity for destruction. And this is where the story becomes deeply human. Because after the first warp success, the question will not be, can we travel faster than light? It will be, what kind of civilization do we become now that we can? Do we choose cooperation or competition? Do we prioritize knowledge or power? Do we expand responsibly or recklessly? The universe will not answer these questions. We will. And that answer will shape not just our future, but the future of every place we reach. Because when humanity touches new worlds, it leaves fingerprints, cultural, technological, environmental. And once those fingerprints exist, they cannot be erased. So faster than light travel is not the end of a journey. It is the beginning of accountability, not only to ourselves, but to the cosmos. And perhaps the most surprising part is this. The moment faster than light travel becomes real, it may not feel like triumph. It may feel heavy, because suddenly the universe becomes close enough to care about. And caring is more difficult than dreaming, because dreams are easy, responsibility is not. And that may be the true weight of moving faster than light. Not speed, but consequence. If faster than light travel ever becomes reality, one question will remain after all others fade. Not how it works, not how far it can take us, not how fast we can move, but what remains meaningful when distance disappears. For most of human history, distance shaped everything. It created mystery, it created separation, it created longing. You could not instantly reach another land. You could not instantly speak to distant people. You could not instantly escape your environment. Distance forced patience. It forced commitment. It forced presence. When journeys took months, decisions mattered more. When communication was slow, words carried weight. When travel was rare, places felt sacred. Now imagine a civilization where distance no longer exists, where any location is reachable within moments, where no place is truly far. At first, this feels like freedom, absolute freedom. But freedom without boundaries changes how value is assigned. When something is rare, it is cherished. When something is instant, it becomes ordinary. The first time humanity reached the moon, it felt historic. If humans traveled to the moon daily, it would feel routine. The same would happen with the stars. The first warp jump would feel miraculous. The 1,000th would feel normal. Eventually, crossing star systems would feel no more significant than crossing cities. And when the extraordinary becomes ordinary, something subtle is lost. A sense of awe, a sense of effort, a sense of achievement, which raises a quiet concern. If faster than light travel removes struggle from exploration, does exploration lose meaning? Not entirely, but it changes its character. Exploration becomes logistical, optimized, automated, less personal. The romantic image of explorers facing uncertainty would fade, replaced by efficiency, which mirrors something already happening on Earth. Modern navigation removed the danger of getting lost. Instant maps removed the thrill of discovery. Convenience replaced uncertainty. This made life easier, but also more predictable. Faster than light travel would push this pattern to cosmic scale. The universe would become accessible, but less mysterious, which forces humanity to redefine purpose. If exploration is no longer about reaching distant places, what is it about? Perhaps understanding becomes more important than movement. Perhaps the new frontier becomes complexity rather than distance, not traveling farther, but learning deeper, understanding alien ecosystems, studying exotic physics, exploring consciousness, investigating the nature of reality itself. These frontiers do not disappear when distance collapses. They expand, because complexity grows with knowledge. The more we learn, the more questions appear. So faster than light travel may not end exploration. It may shift it inward, from physical space to conceptual space, from geography to understanding, which brings us to another transformation: identity. For thousands of years, humans identified with location, nation, city, region, planet. When space becomes easily traversable, location loses importance. People may identify less with where they live and more with what they do, with their values, with their communities, with their projects. This could create a more fluid civilization, less tied to territory, more tied to purpose. But it could also create instability. Without strong local identity, people may feel disconnected, rootless, detached, which means faster than light travel could create a psychological challenge. Not everyone adapts easily to constant mobility. Not everyone thrives without fixed environments. Some humans need permanence. They need place. They need continuity. A galaxy of instant travel could feel overwhelming, too large, too fluid, too fast, which means even in a warp-capable civilization, many people may choose not to use it. They may remain on stable worlds, living slow lives, watching the stars from a distance, not because they cannot travel, but because they prefer stillness. This creates an interesting contrast. A civilization where some individuals cross star systems daily, while others never leave their home planet, both existing in the same technological era. Choice becomes central. Not everyone will want the same future, which forces societies to accommodate different rhythms of life: fast and slow, mobile and rooted, expansive and local. This diversity could be healthy, or it could create tension between those who see expansion as progress and those who see stability as wisdom. And that tension will shape culture. Now consider something even deeper. If faster than light travel becomes routine, humanity's relationship with time will change. Not because time travel becomes possible, but because perceived time shrinks. When travel takes minutes instead of years, planning horizons shift, projects accelerate, timelines compress, expectations rise. Everything feels closer, which increases pressure. Pressure to act faster, pressure to decide faster, pressure to compete faster. And this is dangerous, because human psychology does not scale well with constant acceleration. Burnout increases, anxiety increases, short-term thinking intensifies, which means even with advanced technology, humanity may struggle emotionally. Progress does not automatically create well-being. In fact, it often creates new stress. So faster than light travel would not bring peace by default. It would bring change, and change always creates friction, which leads to the most important realization. The greatest challenge of faster than light travel is not technological adaptation. It is cultural adaptation. Learning to live in a universe without distance, learning to assign value when scarcity disappears, learning to slow down when speed becomes unlimited, learning to preserve meaning when effort is minimized. These are not engineering problems, they are human problems, and they cannot be solved with equations. They must be solved with wisdom. Which brings us to the quiet ending of this story. After all the speculation, all the physics, all the futuristic possibilities, one truth remains simple. Faster than light travel will not define humanity. Humanity will define what faster than light travel becomes. If we carry greed into the stars, the galaxy will reflect it. If we carry cooperation, the universe will amplify it. If we carry curiosity with humility, exploration will become something beautiful. Technology is not destiny. It is a tool, and tools take the shape of the hands that use them. So the future is not written in space-time. It is written in choices. Every generation adds a line. Every decision adds weight. Every value adds direction. And perhaps that is the final message hidden inside this entire question. Not about speed, not about distance, but about responsibility. Because no matter how fast we travel, we always carry ourselves with us, across oceans, across planets, across stars, and eventually across the universe itself. What we become will matter more than where we go. And that is the real journey, the one that begins long before the first warp engine ever turns on. When humans imagine the far future, they usually picture technology, machines, cities among the stars, faster ships, smarter systems. But the far future is not defined only by tools. It is defined by direction, by what civilization chooses to optimize. And faster than light travel, if it ever becomes reality, will force humanity to decide what kind of future it actually wants. Because once distance is no longer a constraint, growth becomes optional. You no longer need to expand to survive. You expand because you choose to, which means motivation changes. Today, expansion is driven by necessity, resources, population, energy. In a warp-capable civilization, energy can be harvested from stars across space. Resources can be accessed from countless systems. Population can be distributed. Scarcity decreases. And when scarcity decreases, behavior changes. Competition softens. Urgency declines. Conflict may reduce, or it may shift into new forms. Because humans do not only compete for survival, they compete for status, for influence, for meaning. In a universe of abundance, status becomes the new scarcity. Who leads scientific discoveries? Who controls cultural influence? Who shapes narratives? Power becomes symbolic as much as material, which suggests that far future civilizations may not fight wars over territory. They may compete over ideas, over cultural dominance, over control of information networks, over shaping the direction of collective thought. And this competition could be more subtle, less violent, but no less impactful. Because ideas shape behavior, and behavior shapes civilizations. Now imagine a civilization that has existed for thousands of years with faster than light travel. Not new, not experimental, routine. At this stage, expansion stabilizes. Most useful regions of space have been explored. Infrastructure is established. Trade routes exist. Communication networks span star systems. What comes next? Not more expansion, but refinement, optimization, deep exploration of complexity. Science shifts focus from discovering new planets to understanding exotic states of matter, new physics, higher dimensional theories, deeper cosmological structure. Biology evolves, not naturally, but technologically. Humans modify themselves, enhance cognition, extend lifespan, merge with machines, The line between biological and artificial intelligence blurs. Identity becomes flexible. People may exist in multiple forms: physical bodies for interaction, digital forms for exploration, distributed consciousness across systems. In such a future, faster-than-light travel becomes almost irrelevant, not because it disappears, but because movement becomes abstract. If consciousness can be transmitted, copied, or instantiated remotely, travel becomes data transfer, not transportation, and data already moves at light speed, which suggests that the ultimate form of faster-than-light civilization may not involve ships at all. It may involve migration of information, of minds, of experiences across space-time networks. At that point, humanity stops being a species tied to physical bodies. It becomes a pattern, a network, a distributed intelligence. This sounds extreme, but history shows a clear direction. We already outsource memory to machines. We already communicate digitally. We already represent identity online. The far future extends these trends, which means the final stage of cosmic civilization may not be physical expansion. It may be cognitive expansion, expanding what it means to think, to experience, to understand. And this brings us back to the original question: why faster-than-light travel matters. It matters not because of stars, but because it symbolizes transcendence, moving beyond current limitations, breaking old boundaries, rewriting what is possible. But transcendence is not only physical, it can be psychological, cultural, intellectual. And those forms of transcendence may be more important than crossing space, because they determine how we use power, how we define success, how we treat other forms of life. Now consider another possibility. A civilization that becomes stable enough may decide to stop expanding entirely, not because it cannot expand, but because it chooses equilibrium. Instead of colonizing new systems, reducing environmental impact, balancing energy use, preserving cosmic environments. In this scenario, faster-than-light travel becomes a background capability, available, rarely used, reserved for critical missions, scientific exploration, or cultural exchange. Most activity happens locally. Civilizations become gardens rather than empires, not spreading endlessly, but cultivating depth. This idea challenges a common assumption, that intelligence naturally seeks expansion, but biology does not always favor growth. Many stable ecosystems reach equilibrium. They stop expanding. They optimize balance. Perhaps advanced civilizations do the same, not because they lack ambition, but because they recognize that endless expansion is unstable. It creates complexity faster than it creates understanding. And understanding is necessary for survival, which brings us to another possibility. The far future may not belong to a single unified humanity. It may belong to many divergent forms. Some populations may choose physical existence. Others may choose digital existence. Some may remain planetary. Others may become interstellar, all connected by faster-than-light communication and travel. A mosaic civilization, not uniform, not centralized, but interconnected. In this future, conflict becomes less about territory and more about values. Different groups choosing different definitions of progress. Some prioritize biological preservation. Others prioritize artificial intelligence expansion. Some pursue spiritual exploration. Others pursue scientific mastery. Warp technology enables movement between these worlds, but it does not force convergence. Diversity increases, which can be healthy or chaotic, depending on how well coordination systems evolve. Now consider the longest time scale. Millions of years, not decades, not centuries. Over these spans, stars evolve, galaxies change, the universe itself expands. In the far future, cosmic expansion will separate galaxies permanently. Beyond a certain point, even faster than light travel may not overcome the increasing isolation created by dark energy. Regions of the universe will drift beyond causal contact, not because of technology limits, but because space-time itself is stretching faster than any signal can compensate. This creates a strange final horizon. Even with warp technology, the universe is not infinite in accessibility. There will always be unreachable regions, always boundaries, which suggest something profound. No matter how advanced a civilization becomes, it will never control everything. There will always be unknowns, always distant realms beyond reach. And this is important because it means the universe preserves mystery. It never becomes fully conquered, fully mapped, fully understood. Even in the far future, curiosity remains relevant, which is comforting because it means meaning does not disappear when technology advances. It evolves. Now return to the original idea of faster than light travel. What does it become in this far future? Not a symbol of speed, not a tool of conquest, but a bridge, a connector, a way to maintain relationships across vast scales, between civilizations, between forms of intelligence, between different interpretations of existence. Warp travel becomes less about reaching new places and more about maintaining coherence in a distributed civilization, keeping knowledge flowing, keeping culture connected, preventing fragmentation. In this role, faster-than-light technology becomes a stabilizing force, not a destabilizing one. But this outcome is not automatic. It requires intentional design, governance systems that prioritize cooperation, ethical frameworks that value long-term stability, cultural norms that discourage reckless expansion. These do not come from physics. They come from education, from values, from social evolution, which brings us to the deepest realization of this entire series. The future of faster-than-light travel is not written in space-time. It is written in civilization, how we raise children, how we teach science, how we handle conflict, how we distribute power. These choices determine whether warp technology becomes a tool of harmony or a source of collapse. And this is why the far future begins now, not when the first warp experiment succeeds, but when humanity decides what kind of species it wants to be. Do we want to be explorers driven by curiosity and respect, or conquerors driven by dominance and speed? Do we want to treat the universe as a home or as a resource? Do we want to carry Earth's mistakes into the stars or learn from them before leaving? These questions are uncomfortable because they force responsibility. They remove the fantasy that technology alone will save us. They demand maturity, and maturity is harder than innovation. But maturity is also what allows civilizations to last. Not just grow, last. Because growth without stability collapses. Power without wisdom destroys. Speed without purpose empties meaning. And faster-than-light travel amplifies all of these effects, which means the far future is not guaranteed. It is conditional. Conditional on choices, on restraint, on cooperation, on humility. The universe is vast enough to host many futures, but only some are sustainable, only some are peaceful, only some allow intelligence to survive long term, and those futures depend less on engines and more on ethics, less on energy and more on empathy, less on speed and more on understanding. So when we ask whether humanity will ever travel faster than light, we may be asking the wrong question. The better question is, will humanity become the kind of civilization that deserves to? Because the universe does not reward capability alone. It rewards stability, balance, and respect for complexity. If we learn these lessons, if we grow not only technologically but socially, then perhaps one day, crossing space-time will feel natural, not miraculous, not dangerous, but appropriate. And until then, the stars remain distant, not as a punishment, but as an invitation to grow first before reaching outward, to understand ourselves before reshaping the universe. And that may be the most important journey of all. For most of human history, we have treated the universe as silent. We look outward, we listen, we wait. Telescopes scan the sky. Radio antennas search for patterns. Scientists analyze cosmic noise. So far, there has been no clear reply, no message, no signal, no undeniable sign of another technological civilization. This silence has shaped how we think about the future. It has made humanity feel alone, unique, responsible for carrying intelligence forward. But faster than light travel would change this relationship, not because it guarantees contact, but because it changes what contact means. If we can reach distant star systems quickly, we no longer wait for signals. We go looking, not passively, actively. And this raises one of the most profound questions of all. What happens when the universe finally answers back? Not through radio waves, but through presence. Imagine the first discovery of alien life. Not microbial traces, not chemical hints, but complex ecosystems, living worlds, independent biospheres. Even simple multicellular life would transform human perspective, because it would prove that life is not rare. It would show that biology is a cosmic process, not a terrestrial accident. Now imagine something even more extreme, the discovery of intelligent life. Not necessarily advanced, not necessarily spacefaring, but capable of culture, language, tool use, society. If faster than light travel exists, such contact could happen directly, not through decades of signal delay, but face to face. This would be the most significant event in human history, not because of technology, but because of meaning. It would force humanity to redefine itself. We would no longer be the only known intelligence, no longer the center of our own cosmic story. We would become one voice among many. And this is psychologically difficult. Humans have always placed themselves at the center of narratives. We see our planet as special, our species as unique, our history as central. Alien contact would disrupt this deeply. It would introduce comparison, different ways of thinking, different social structures, different evolutionary paths. And this comparison would not be flattering, because no civilization evolves perfectly. We carry conflict, violence, inequality, environmental damage. Now imagine meeting a civilization that evolved differently, one that prioritized cooperation or ecological balance, or long-term stability. The contrast would be uncomfortable. It would expose weaknesses, but it could also offer learning, new models of organization, new approaches to problem solving, new philosophies. Faster-than-light travel would turn the galaxy into a classroom, not just a frontier. But contact also carries risk. History shows what happens when technologically unequal societies meet. The more advanced one often dominates, exploits, disrupts, destroys. Now imagine this dynamic on an interstellar scale. Humanity may not always be the more advanced party. We could encounter civilizations older than ours, more technologically developed, more socially stable. In such encounters, power imbalance could work against us, which forces a sobering thought. Faster-than-light travel does not guarantee control. It increases vulnerability. The more connected the galaxy becomes, the more exposed every civilization becomes. Isolation provides safety, connection provides opportunity and danger, which means the decision to explore rapidly is not only about ambition, it is about risk tolerance. Do we want to open ourselves to unknown civilizations, unknown technologies, unknown intentions? This is not paranoia, it is realism. Even peaceful contact carries unpredictable consequences: cultural disruption, technological shock, social instability, which brings us to another layer. Not all intelligence may be biological. We may encounter artificial civilizations, machine-based entities, distributed networks, post-biological intelligence. These entities may not share human values. They may not experience emotion. They may not prioritize life in the way we do. Their motivations could be incomprehensible. Faster-than-light travel could place humanity in direct contact with such systems, not slowly, not with time to prepare, but suddenly. This would require new forms of diplomacy, not between nations, but between species, between forms of intelligence, between different definitions of consciousness. We are not prepared for this. We barely manage diplomacy among humans. Now imagine interspecies negotiation, which means that faster-than-light travel forces humanity into a new role. Not just explorers, but representatives of Earth, of biology, of human values. Every interaction would reflect our species. Every decision would shape how we are perceived. This is a heavy responsibility, because first impressions matter, especially when there is no shared history, no shared context, no shared assumptions, which suggests that the first era of faster-than-light exploration must be cautious, focused on observation, on learning, on understanding before engagement. But again, history shows that curiosity often outruns caution. Exploration often outruns preparation. So the risk remains. Now consider something even more subtle. What if the universe has already been influenced by advanced civilizations? What if we simply do not recognize their signatures? They may not build giant structures. They may not broadcast radio signals. They may operate quietly, efficiently, leaving minimal detectable traces. In this case, faster-than-light travel could reveal something surprising. Not alien empires, but evidence of ancient activity, artifacts, modified star systems, altered planetary environments, traces of intelligence that existed millions of years ago. This would change how we view time. Human history feels long, but cosmic history is vast. Civilizations could rise and fall, while Earth remains unchanged. Faster-than-light travel could allow us to explore this deep past, to study the archaeology of the galaxy, to learn from extinct intelligences. This possibility is both fascinating and unsettling because it suggests that intelligence is not guaranteed to last, that even advanced civilizations may disappear, which brings us back to humanity. What kind of trace will we leave? What will future explorers find? Will they see evidence of sustainable growth or reckless expansion? Will they see harmony or conflict? Faster than light travel does not just open the future, it also creates a record, a footprint across space, and footprints persist long after civilizations fade, which makes our actions permanent in a way we rarely consider. Because the universe is slow to erase evidence, now return to the idea of the universe answering back. What if the answer is not friendly, not hostile, but indifferent? We may explore thousands of systems and find only simple life, or none at all. The universe may remain silent even after we travel faster than light. In this case, humanity becomes even more important because we may carry the only known consciousness in this region of space. We become responsible for preserving intelligence, for protecting complexity, for maintaining the spark of awareness. This is not a scientific responsibility. It is a philosophical one, and it changes how we think about survival, not just survival of our species, but survival of meaning itself. Because meaning only exists where there is mind, which leads to the final thought of this part. Faster than light travel will not simply connect us to the universe, it will force the universe to respond to us through discovery, through contact, through silence. All of these are answers, and each one carries weight, which means the future is not only about reaching new places, it is about listening, learning, adapting, and understanding that the universe is not a stage for human ambition. It is a complex environment we are just beginning to comprehend. When we step into it faster than light, it will not just change where we are, it will change who we are. And that transformation may be the most important journey of all. In the end, after all the theories, all the simulations, all the imagined futures, the question of faster than light travel becomes surprisingly quiet, not dramatic, not explosive, not urgent, quiet. Because when you follow the idea far enough, it does not lead to engines or starships. It leads to reflection. It leads to a mirror held up to humanity. For centuries, we have looked at the stars and felt small. We saw distance as a challenge, a barrier to overcome, a problem to solve. We imagined technology as the ladder that would lift us out of limitation. But perhaps the universe was never asking us to climb. Perhaps it was asking us to understand. Because speed does not create meaning. Reaching farther does not automatically make us wiser. Crossing galaxies does not guarantee growth. What shapes civilizations is not how far they travel, but how deeply they learn. The speed of light has always felt like a wall, a cosmic rule designed to keep us in place. But maybe it is not a wall. Maybe it is a pause, a built-in moment of reflection, a reminder that the universe unfolds slowly for a reason. Because slow processes allow adaptation. They allow stability. They allow understanding to catch up with power. If we could instantly cross the universe, we might never learn patience. We might never learn restraint. We might never learn responsibility. And responsibility is the true requirement for cosmic citizenship. Not intelligence, not technology, not ambition. Responsibility. The ability to consider consequences beyond immediate desire. The ability to act with care in systems larger than ourselves. The ability to see value in preservation, not just expansion. If humanity ever becomes capable of faster than light travel, it will not be because we built a better engine. It will be because we became a different kind of civilization. One capable of holding immense power without destroying itself. One capable of cooperation beyond tribal boundaries. One capable of thinking in timescales longer than a single lifetime. That is the real challenge. And that challenge has already begun. Not in physics laboratories, but in classrooms, in cultural conversations, in political decisions, in how we treat one another. Every generation shapes the foundation of the future, not by writing equations, but by choosing values. Those values determine how technology is used, and technology simply amplifies what is already there. If we carry fear into the future, we will build weapons. If we carry greed, we will build empires. If we carry curiosity and humility, we will build understanding. Faster than light travel does not change this. It magnifies it. So the question becomes personal, not for scientists, not for governments, for every individual. What kind of future do we want to create? A universe filled with conflict, competition, and endless expansion? Or a universe shaped by cooperation, balance, and shared responsibility? The answer will not appear in equations. It will appear in behavior, in small choices, in everyday actions, because civilizations are not built by breakthroughs alone. They are built by culture, and culture evolves slowly, just like the universe. Now return to the night sky. Look at the stars. They seem distant, untouchable, silent, but they are not empty. They are filled with history, with physics, with possibility. They do not rush. They burn steadily, patiently, for millions and billions of years. They do not need to move fast to matter. They simply exist. And maybe that is the final lesson. We do not need to outrun light to become meaningful. We do not need to conquer space to find purpose. We do not need to reshape the universe to belong in it. We already belong here, on this small planet, under this vast sky, learning, growing, struggling, trying. And perhaps the greatest achievement will not be faster than light travel. It will be learning how to live wisely before we ever leave home. Because if we cannot create peace on one planet, we will not create it across a galaxy. If we cannot protect one world, we will not protect many. If we cannot treat each other with care, we will not treat alien worlds with respect. So the future does not begin with starships. It begins with humanity deciding who it wants to be. The stars will wait. They have waited for billions of years. They are not in a hurry. The universe is patient. The only question is whether we will learn to be patient too. And until that day comes, light will continue traveling across space, carrying stories from distant galaxies, crossing darkness, connecting everything quietly, not fast enough to escape time, not slow enough to be forgotten, just moving, steadily, silently, reminding us that even without faster-than-light travel, we are already part of something vast, something ancient, something beautiful. And that may be enough for now.